we were somewhere on this page. Every one of the three classes were somewhere on here. And I think it just would be prudent after being gone so long to at least talk about what we were doing. I want to say Friday. Yes, you guys, your last day here was Friday, and then we had conferences on Monday. So we are on the page that's talking about multiplicity of zeros. And we said multiplicity of zero of a polynomial function just means that if we see this, and we know there's not another factor of x minus 2 anywhere else in the polynomial, then this is the multiplicity for that zero. And the zero for this one would be 2, 0. But more than that, we want to know, is it going to cross at that point? Is it going to bounce and be a tangent at that point? What's going to happen? And that's what this 3 is going to do for us. If that's odd, that tells us that it's actually going to cross the x-axis at that 0. If this multiplicity up here is a 4, well, then that's even, and that tells us it's going to be tangent. So it's going to hit the x-axis and it's going to bounce off. So, moreover, multiplicity explains the behavior was in this little box down here. And that's exactly what they did. But usually they'll describe it as it behaves linearly. If it is odd, that just means like 1. So it's going to cross the x-axis. And I know in your algebra book it talked about how if it isn't even, it behaves kind of like quadratic. That's because that's what it's doing. It's bouncing off at that point. So if a polynomial function f has a real zero c of odd multiplicity, the graph of f crosses the x-axis at that point. And like it says, that should help us figure out that means that we're going to change signs at that point. And that's because the y's either were positive and now they're going to be negative, or they were negative and now they're going to be positive. So we watch for that sign change when we're using the graphing calculator. If a polynomial function has a real zero c of even multiplicity, then the graph of f does not cross the x-axis at that point. It doesn't change sign, it changes direction. You know, if it was going down, it's going to go up. If it was going up, it's going to go down. So sketching the graph of a factored polynomial down here is where we're at. And this is in factored form. So it says state the degree and list the zeros of this function, and then state the multiplicity of each zero and whether the graph crosses. So without graphing, with the graphing calculator, which we will in a little bit, but just to start off with the basics of this function, we would know them. And that's from the fact that we have a cubic and a squared here. And so in the process of expanding all of those and multiplying those out, we would end up with an x cubed from this front factor, and then an x squared from the back one. So x cubed and x squared, that would give us an x to the 5th. So that means this would be a degree 5 polynomial. Now there are no negative signs in front of this thing, so it would be a positive x to the 5th, and that means we know the end behavior of this. Because it is odd, we know that it's going to do this and this for end behavior. Now, in between there, stuff's going to happen, and we want to know what is that stuff. And that other stuff comes from taking a look at what we have for those factors and their multiplicity. So, state the degree, already did that. List the zeros of the function. The zeros would be negative 2, 0, because negative 2 plus 2 would give us a 0. And that one would have a multiplicity of 3. So think about what that means. That means the graph is going to cross the x-axis at negative 2, 0, because that is an odd multiplicity. And then we have a 1, bless you, 0 back here. But that one's a multiplicity too. So that one's going to be a bouncer. And all of that has to fit in with what I already know about my end behavior. So we've got the multiplicity, and then it says, tell whether or not it crosses it. Well, this one is going to cross. Right there. And then sketch it by hand. So now they're saying, all right, we know about the end behavior. We know where these zeros are going to be, and we know whether or not they cross or not. Let's just use all that information. So at negative 2, 0, we know it's going to cross. And at 1, 0, it has a multiplicity of 2, so it's not going to cross. And this has to be its end behavior. So that means I absolutely know the graph is also know it has to come up here somewhere. I don't know how high. And turn around and then bounce off the other zero. Now the part that I have that's dashed there is the part that, yeah, we have to use the graphic calculator for, or make a little table really briefly and plop in maybe 0 and -1 and see what we could get quickly for those two. But let's just grab the graphic calculator and take a look at this one. And make sure that what we know about the math is actually going to show up. And if you're worried about the fact that this is not expanded in standard form, don't be. Your calculator can handle that just fine. So we'll put the parentheses and all in there. And we'll just let the calculator handle it. Oh boy, did I not get that in there. X plus 2 to the third. So when we take a look at that, we see, okay, there's something kind of goofy happening right here where it like levels out a little bit. But it does go up, bless you, and then it does come back down like we knew it would. Now, the other part of this they're not too worried about because they just wanted us to make a sketch by hand. But we certainly know we use the graphic calculator to find out where that max is on here and go from there. I didn't even write it down because it's not important with this problem. But you might want to plop, like I said, put the 0 in here. 0 plus 2 is 2, 2 cubed is 8. And then 0 minus 1 is -1, and -1 squared is 1. So that would give us an 8. 1, 2, 3, 4, 5, 6, 7, 8. That's looking something like that. So it wouldn't take very long. It wouldn't take long to get the calculator. But there it is. And we answered everything they wanted, degree. So we used that end behavior to figure out where to go with this graph. And then we found the zeros, found the multiplicity of those zeros, whether or not it crossed or not at those intercepts. And we just had the one that it was crossing at, and then sketched the graph by hand. So there's still that one little piece there that we have to use the graphic calculator for, or, bless you, just basically plug a number in so you can see where it is. That's going to be that local max. So now, on the next page, we have a new theorem that you were not introduced to in Algebra 2. But it's a theorem that just, it won't make sense, logical sense with what's going on. The intermediate value theorem explains that a sign change implies a real zero. What on earth are they talking about? As our graph crosses the x-axis, the y's change sign. Down here, our y's are going to be less than 0. They're going to be negative. Up here, they're going to be positive. And that, in fact, is something we have to have happen when we use our graphic calculator to find the zeros, or it gives us a message, no sign change. And then we know we didn't plug it in the way that we were supposed to. So this intermediate value theorem is just a theorem that says, hey, this is what we know what's going on, but let's talk about it in terms of algebra. So if a and b are real numbers with some a value less than b, and if f is continuous on the interval from a to b, and that just means, again, no breaks, no jumps, nothing like that, then f takes on every value between f of a and f of b. Well, that means all of the y values are being used in this interval. And then it says, in other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some number c in the interval from a and b. In particular, if f of a and f of b have opposite signs, one of them is negative and the other is positive, well, then there has to be a 0 somewhere in there. If your y's were negative down here, and then all of a sudden your y's became positive, there is some 0 there. It might not be a But there has to be a 0 there because this is continuous over the domain. So down here we have a drawing that's a little bit better than my little sketch there. And this is just showing exactly that. You know, we've got y sub 0 equals 0. This is the x-axis. I guess that's probably not as visually, you know, they didn't do a good job of saying, hey, this is the x-axis right here. If you didn't look carefully, you wouldn't see that little x down there at the end. But they're saying the exact same thing that I did with my little drawing, which is, hey, if this blue graph is defined and continuous over the interval from A to B, right here to here, well, at some point, it's crossing the x-axis because the y values down here were negative and the y values up here were positive. It's crossing. It has to be. So now example 7 says, using that intermediate value theorem, explain why a polynomial function of odd degree has at least one real 0. All right. Polynomial function of odd degree. So I think about what polynomial functions with odd degree have, and it's either going to look like this for n behavior, or it's going to look like this. In either case, it has opposite n behaviors, so it has to cross the x-axis somehow. But this is saying, using that intermediate value theorem, explain that. All right, so here's how we're going to start. F, whatever the polynomial is odd. Right away, I drew that picture. I know to draw that picture because those are the only two behaviors that our odd multiplicity polynomials will have. So, if it's odd, then the limit as x approaches negative infinity of f of x, is it exactly the same as the n behavior as we go to the right forever? It's the opposite, isn't it? So typically if we want to say it's going to be the opposite, we'll just put a negative in front of it, and that's what we're going to do here. They have to be the opposite. That's what we know. That's what that odd multiplicity tells us about this. So there exists some, and now I'm just going back to that intermediate value theorem because they said I had to use it. Some A and B such that A is less than B. So that's what the theorem said had to happen. We had to have an A and a B. A should be less than B in this case. And such that f of A and f of B have opposite sides. So this is just the logic that comes from the picture that we have. We know they're going to have opposite sides. Now, there was something else that we had to have in order to use the intermediate value theorem. It said, if A and B are real numbers with A less than B, and f is continuous on the interval from A and B. So I go back to the problem and say, how did I know this was going to be continuous? And it's one of those little hidden things like you had to do back in geometry, where you're looking at it and you're saying, there's got to be something there that was supposed to tell me something. We've already used the fact that it's odd. What else have we defined in this section so far that's supposed to give us information? Well, yeah, it's a polynomial function. Remember, polynomial functions, and I think it's 2 pages back in your notes right at the top. It says, polynomial functions are defined and continuous for all real numbers. That's what we need for the intermediate value theorem. It said it had to be continuous. So, f is a polynomial function. So it is defined and continuous on, oops, that's not really a square bracket and b are real numbers with a less than b, and f is continuous on the interval from a to b, then f takes on every value between f of a and f of b. So that means we have met all the good stuff that the intermediate value theorem needed. So we would say the intermediate value theorem states just go back up to that and say that for some number c, in that interval a to b, f of c is going to equal 0. Explain why a polynomial function of odd degree has at least one real 0. Well, if f of c equals 0, then it has one real 0. I'm going to have to scoot this out because, as usual, I wrote way too big. Here's our usual wrap it all together thing that therefore just it's with every paragraph proof it's just saying, okay, what did we want to do here? Therefore c is a real 0 of f. And again, this is where people get nervous because they're like, are we going to have to do that? No, we're not going to have to do that. We're going to try to figure out where that 0 is. And that we're using the graphing calculator for, and or factoring. You know, any way that we can find it is what we're going to do. But we need to know it works, and we need to make sense of it. And so that's the reason we go through that problem, is to say, okay, in terms of algebra, how can we write this and have it make sense? So example 8 says, we're going to zoom in on some hidden behavior. And it says find all the real zeros of f of x equals, and then we see a monster polynomial function there. Now, first thing to try would be to factor. But we have 1, 2, 3, 4, 5 terms. We've never been able to factor with 5 terms before. You know, the most factoring we've ever done is with 4, and that's if it's factorable by grouping. So we don't really have a choice here. We're going to have to grab the graphic calculator and find the zeros for this one. So let's get this in. Plus 0.1 x to the third minus 6.5 x squared plus 7.x minus 2.4. So there it is. Well, we're supposed to find all the real zeros. And I think there's some pretty obvious ones. Bless you. So the first thing we do is second trace, number 2, and I've always done these left to right. And now what I'm watching for up there is, when do my y's seem to get close to 0? So now I'm to the left side of that intersection, and I press enter. Arrow to the right once, enter, enter to guess. So there's our first 0, negative, well, it would round up to negative 3.100. There's our first one. And if this were on a test, we might have to go ahead and change this, because I could see in the initial graphing of this that I'm way off the grid. But what we're caring about is the zeros, and this is just kind of a little helper for us here. So then the next 0 is kind of, well, hidden. It's like, is that just 1 0, or is it crossing 2 times? So this is where I go back to zoom box, zoom number 1, and where are you, Blakey? Right over there. And along with the in that location, see those zeros. And then the box. This is the hidden hard to see that there were going to be 3 more zeros there. In fact, from the initial Zoom 6 that we had, we might have said, hey, it looks like it's crossing at the one on the left, but then at the other one, maybe it's just bouncing off of there. So second trace, number 2, we will get this one. Just working from left to right, and that one ended up being really nice, 1/2 0. 0.500. And then 2 more. I'm probably going to do Zoom box again. Just so that this is really, really obvious. Just take the zeros there. Second trace, number 2. And this guy over here. To the left, enter, right, enter. Oops. Look at the finger here. Picking up that mask. $1.1330. One more. Anything the calculator doesn't know below and above, it just goes left to right. So this one's going to be backwards. Below it to the left and above it to the right. 1.3670. Do you have to make a sketch? No, you don't have to. It said find all of the real zeros, but what we had to see was that there was some hidden behavior here. So we might want to just make a little sketch of the fact that those are really, really close together there. Right, this is 6. Something along these lines. Okay, now it's not drawing. There we go. To show what we saw there. But again, the drawing wasn't important. All right, so zeros. Now, how about working backwards? What if they give us the zeros and say, write a polynomial function in standard form? Did this last year, but it's been a while, so let's take a peek. This one says, let's find a polynomial with zeros at 2, -3, and -4. Well, to get these, they had to come from some x minus h. So we're going to think backwards to write this. So if our 0 was a 2, what did this look like? X minus 2. How about this one? What was that one? X plus 3. And this one. Now, even though it doesn't state that it needs to be in standard form, we have to write it in standard form. We're not going to stop like that. We want to take a look at it and see what the polynomial is going to be. So usually what we do is just we pick any 2 of them, and usually it's the back 2 because it's the easiest way to go with this. And just FOIL those 2 together first. So we would have f of x equals the quantity x minus 2. And if you just quickly in your head do the outside times outside plus inside times inside, you can go directly to x squared plus 7x plus 12. Now, that's not the part that I was worried about everybody remembering how to do. Do you remember what to do after this? What do? Distribute, right. So you're going to take the x times everything back there. And then again with a -2 distributed. And then of course we clean it up a little bit by combining like terms. So f of x equals x cubed plus 5x squared minus 2x minus 24. If I gave you one of these right now with 3 zeros, 4, 3, 2, 1, 0. So that's coming back good for everybody. Because this next one is tougher. Why? Because the zeros are nastier. That's why. So not the 2 in the front. That's not going to be a problem. I'll just name this one g of x instead of f of x like we did the last one. The 2 is not a big deal. Whoa! Look at these two. So take, well, the last one wasn't difficult because all I did was think x minus h. Well, this is going to be a little more work, but it still has to be x minus 1 minus the square root of 3 and x minus 1 plus the square root of 3. Right away, your algebra instinct should kick in and you should say, okay, wait a minute, though. That means if there's subtraction in front, I should really distribute that because that's going to change some signs. So I'll leave this alone for a minute, but this is going to be x minus 1 plus the square root of 3 and x minus 1 minus the square root of 3. And now comes the tipping point of this problem. Because we could do this one by distributing. It would be super nasty. So what we do at this point is we say, gosh, if I could figure out a way to group those last two somehow so this is easier to multiply, that would be really, really helpful. So let's see. Well, it'd be pretty easy to take x minus 1 times x minus 1. That wouldn't be a big deal. Okay, why isn't it showing up when I'm writing? Come on, smart board. There you go. Oh, no, they all show up. Fabulous. Now, I think, would that be helpful? Oh, sure it would. Because, look at this. This one has a sum, and this one has a difference. And that's that difference of 2 squares pattern when we're factoring. So that means if I multiply these together right now, there's not going to be a middle term. Because outside times outside would be minus the square root of 3 times x minus 1. And inside times inside would be plus the square root of 3 times x minus 1. And that's a math I really don't want to do. So that would be the best way to group this. So I'll have x minus 1 times x minus 1, which is, of course, x minus 1 squared. But outside times outside and inside times inside are going to drop out. And then I'll have a positive square root of 3 times a negative square root of 3, which is going to be minus 3. Square root of 3 times the square root of 3 is the square root of 9, which is 3. Now, it's not done, but at least I'm not going to have any more radicals in it. So the next thing to do would be to figure out, okay, do I remember how to multiply x minus 1 squared, and can I just write that down without this step? Or do I have to FOIL it? And most people generally write it out twice and then just kind of think through it with FOIL. So we'll have x minus 2, and then we'll have x squared minus 2x plus 1 minus 3. And now it's getting better and better. We'll have x minus 2, x squared minus 2x minus 2 in the back. And now it's just like the last problem where when I got here and asked you how to do it, you said, well, you distribute it. Yeah, that's what you do. You distribute the x, and then you distribute the negative 2. So we've got g of x equals x cubed minus 4x squared plus 2x plus 4. So like I said, right here, is where you make the decision that makes all the difference. Because if you don't notice, hey, I can make this a sum and a difference problem, this gets really, really messy. You get the same answer in the end if you're careful, but it's going to take you forever to get down to what we have here. It's not that it can't be done. In fact, with my Algebra 2 students, I always do one of these with distribution first to show how noticing that pattern helps out a lot with these problems. So those are fun. Now we go on to little word problems, but they're not. Now are they word problems, but not, because what we have to do here is just remember what we did in Algebra 2. We did a lot of these box problems, this modeling, which is another part of our objective, and it was the part we really didn't get to before our break, and that was modeling polynomial functions. So designing a box, we've got Dixie Packaging Company, and they contracted to make boxes with a volume of approximately 484 cubic inches. Squares are to be cut from the corners of a 20-inch by 25-inch piece of cardboard, and the flats will be folded up to make an open box. And it says see figure 2.31, so that must be a drawing. Well, hopefully did you get the drawing in your notes? Oh, they're probably just using the same drawing that we have for the one below, so you can look at that. Yeah. So basically, we've got this piece of cardboard that is 20 by 25 inches. And once again, I'm going to cut these little corners out, not knowing what each of those is going to be. And when we make that, we realize, well, whatever it was before, once we cut those x's out, it's going to be minus those two x's. So since they're talking about volume, you have to think, well, length times width times height. So it's going to be 20 minus 2x times 25 minus 2x. But then what's the height of this thing going to be? What goes up? Yeah, it's x. It's x. Now normally, we'll just leave that x and do the rest of the problem first. So take that 20 minus 2x times the quantity 25 minus 2x and see what you get. So 20 times 25, that's going to give us 500. And then outside would be negative 40x, inside would be negative 50x, so minus 90x. And then last times last would be plus 4x squared. And then we'll multiply everything by x, and finally we'll put it in standard form. So 500x minus 90x squared plus 4x cubed. And just rearrange that. All right, so we wrote a model. There's our model. Now, they want to make the boxes 484 cubic inches. Okay, so that means we need 484 over here. Like so. And what we want to do is find out where the solutions, and the solutions are the zeros. So we would subtract 484 from both sides. Just go after the zeros. That's what we would have to do here. So, solve graphically and numerically. Well, let's get it in there, and then let's talk about what our x's and our y's would be. 4x to the third minus 90x squared plus 500x minus 484. Window. What we said was, pretty obviously, you can't cut out more than you already have. So as I look at 20 minus 2x, I'm thinking to myself, well, 20 minus 2x has to be greater than 0 in order for this to have a volume that's not 0. Well, we could go ahead and add 2x to both sides and divide 20 by that, and we'll get 10. So if this is a 10, 20 minus 2 times 10 is going to give us 0 for one of the dimensions. So it looks like that would be the highest we'd be able to go for our x's, because if we use a 10 here, we'd still be okay. So our x's from 0 to 10 should be just fine. But our y's, well, we have to be able to see what we had for a y there, but we might not want to go all that way anyway. And that's because we're going to be talking about, well, let's just try. Let's give it a try. Let's put the 480 for it. That's not too bad. We can use that. So when we look up here, we see there's actually two spots that would be zeros for both of us, and that means they have two possibilities. So second trace, number 2. And I might want to put some negatives on my y's, but if I can watch blinking and see that the y's go below the x-axis, there's my negatives, press enter. And to the right is above for the positive. So there is the first choice they have, 1.222 inches. Above, because the y is positive, enter. And I'm just going to hit the right arrow until I get to a negative y value. There it is. And enter your guess. 6.871. So those are the two possibilities. Now, what size squares should be cut from the cardboard? Either one of those. It's up to them. And when they put those numbers in there, one of these boxes is probably going to be tall and skinny, and the other one will be short and fat. But it'll be totally up to them which they want to use, because we ended up with 1, 2, 3, 4, 5, 6, 2 different possibilities for that. So they can go either way. And usually the customer will let them know which one they want. The short and fat or the tall and skinny, depending on what they have for space to store those boxes. So example 10, we're doing the same type of thing. This says we've got an open top box made by taking a piece of cardboard, but this time it's 20 by 40. And we're going to fold it up on its sides, and we need to write an equation. So I'm going to have you help me out more with this time. What should we use for one of the dimensions? So what's the third dimension? X, yeah. So put that here. Go ahead and do the FOIL on that one. See if we can all end up in the same place. Did say have to name it B of X this time. So just B is not cut. Suppose I should have read those directions. Write an equation in expanded form of polynomial function B of X, representing the volume of the box in terms of X. Everybody okay so far? 4x cubed minus 120x squared plus 800x. B says, let's talk domain. What is the domain of B of X? So for what values of X would we end up having this as a positive value that we would be able to use? So there are actually two, and I wanted to go over this again. I was thinking about this last night when I looked this over there. Remember we talked about implied and relevant domain? And that seems like forever ago, so that was one of the reasons I wanted to talk to you about this. If we didn't know that this were a word problem about boxes, the implied domain would be from negative infinity to infinity. And you'd say, hey, you use whatever you want. But we do know that avoid, we know we could have 0 for a volume, so it's a possibility, but we would rather not use a lot of numbers that we don't need to use. So thinking of what I talked you through with the last one for finding that top number for the domain, what should we use? And this is the thing with the book always says, I'm with you, Hannah. I would probably make that a parentheses instead of a bracket. But the book always says technically you could have a 0 volume. It's negatives that you can't have. So the book always starts with 0. But I'm with you. It's like, why do this problem if you're going to put a 0? What about this? Should we just put a bracket? Yeah, just put the bracket so that we're all doing exactly the same thing. Did you find the number you wanted to use for your x cutoff? Come back up here and say 20 minus 2x has to be greater than 0. 40 minus 2x has to be greater than 0. And basically find the smallest one. And that will be your cutoff. So what is it? 10, yeah. Because if we add the 2x to both sides here, and then divide, that's going to say x has to be less than 10. This one, you can add the 2x and divide, but this says x has to be less than 20. Well, it's like we already know it has to be less than 10, so that's what we need to use. So that would be what's called our relevant domain. That's the one that makes sense for this problem. Oh, and we've answered the question because it says that what values of x make sense in the context of this problem. And again, I'm with you, Chance. I would prefer that the book went both ways if it's going to do that, that they used brackets here and then they used brackets over there because they are saying that 0 is a possibility, but they always do it this way. And I'm not quite sure what their logic is there. So you know what? If it is on the test, I'm going to take it both ways. Because like I said, I would use parentheses for both of those. If you're talking about box, you don't want volumes. So I would use parentheses on that. And have that go this way. It is there. There are just some points in this book that things just don't kind of ring true. You know, if they're saying it's okay to have 0, why not use the 10 on the end of that? But they don't. They leave it out. C says, if the volume of the box is to be 1,500 cubic centimeters, show that the box can be constructed in 2 different ways. Well, we ran across that with the last one. So let's make this 1,500 for the volume. And then move the 1,500 over. And let the calculator help us out with where that should be. And we already have the 0 to 10, but we need to be able to see that 1,500. Maybe go a little bit higher than that. Oops. There we go. Well, all I see is an itsy bitsy little dip there. So what that tells me is I don't want all of those y's on there. A little better look. I mean, you could find it either way. But let's just do that. Let's just stop and find second trace number 2. Hopefully we won't get too lost. What he says is right there, 50. I'm moving blinking until I see a negative on the y. And I'm going to the right until I see a positive. So 3.486. Inches. And the other one, second trace, number 2. So keeping the line positive. Oh, look at that right there. It's 50 volume of the box is to be 1,500 cubic centimeters. Show that the box can be constructed in 2 different ways and find the exact dimensions of the box in each case. Well, that means we have to actually plug this in and find the length, width, and height. Oh, I didn't even keep going. Once I saw that it was 5-0, then it was perfect. And you could always just go to the table for that one also. You know, did yours come out with scientific notation? Oh, I see what you mean. Remember, we put the 1,500 there and we moved it over to the other side. And we also talked about relevant domain. And since we can't be outside this, yes, there's a third 0 out there somewhere, but it's going to be way more than we would be able to use with this relevant domain. So we're not even going to bother finding it. So now, just to save some time, because I'm sure I'm getting close to it. I'm going to tell you that if we plug these back in, we would get 3.486 inches by, and what I mean by plugging it back in is put it into 20 minus 2x. That would give us 13.028 centimeters by, and then if we plugged it into 40 minus 2x, we get 33.028. Oh, this one was in centimeters. I wrote the first one. That inches in my brain from the last problem we did. There we go. And then the other one is easier because we had the 5. So it could be 5 centimeters by, and again, you just go back up and plug it in. So 2 times 5 is 10. 20 minus 10 will be 10. Sorry, Hannah? No. And then the last one will be 30 centimeters. And yeah, you could make a little sketch if you want to, but really you use the graphic calculator for the whole thing to find that. It's the algebra that we need to see for the polynomial. And after that, then things are fine. Now, D says, what dimensions would give the maximum volume of the box? Oh, well, we didn't find that yet. Because we're not at the highest point. The highest point is up there. So second trace, number 4, there's not a whole lot to do here. Oops, I didn't go far enough. Second trace, 4. There we go. Now it's starting to go down. Left side of the hill, right side of the hill. Yes. So that would give the maximum, 4.226. I should believe it was D. I started to write all over the top there. And that would be centimeters. Now, why isn't that the maximum volume that they used? Well, when you pick up a can of Coke, Pepsi, whatever it is, they're not trying to make sure that they're using the least amount of aluminum possible. But I know that seems weird because everybody's into recycling, and why wouldn't they? And that's because if they use the least amount of aluminum possible to get you that can, you could not hold that can and walk around with it because it would be short and fat. And so what they decided to do was make it so it'll fit in your hand. So if you're driving or whatever it is you're doing, you can have a can of pop in your hand. And it's the same thing here. They're not asking for maximum volume. They have certain things that they need to meet, certain dimensions that they want to have. And so this is the maximum that we see here. So if we took that 4.226 and put that back in, we would get 11.548 centimeters. And then 31.548 centimeters. So that would actually give them the maximum. not in this case, and that's because we moved over that 1,500 to do this. So what we would have to do is actually put these all back in and then multiply them together. It would actually come out to 1,539.601 cubic centimeters. So it's all about what did they want to happen here. And they didn't ask for the maximum. They just said, hey, what would the possibility be to meet the conditions that they had when we started? It is the max volume, yeah. And so we're getting this. And like Hannah said, she said, so that Y value doesn't mean anything? No, it doesn't, and that's because we moved the 1,500 over to the other side. If we had left it there and graphed it to find the intersections, then we would be able to use the volume, but not this way. All right, and that leaves us with a couple of pieces of regression that we need to do, which, you know what, we could probably do in these last 2 minutes, but then you wouldn't have time to write them down. So I'm going to save that for tomorrow, and we're going to have 2 days to review anyway, so we'll just do the regression tomorrow. And you know what? I bet you could probably do 2, 3, day 3 on your own anyway, because we have already done, oh, wait a minute. Nobody in here came from college algebra. But some of you probably did not do the section that had nonlinear regression last year in Algebra 2. We've done that before though this year, haven't we? Didn't we already do a quadratic regression? Okay, so you could probably make your way through it anyway, you know. But if you can't, then hold off. Tomorrow it'll be like a 5-minute lesson on it, and I'll be able to show you how to do those other regressions. So it's not a big deal